Welcome again to this session of Shadow the Scientist, Astronomy Night at the International Gemini Observatory North for the CENTA community of teachers and students. My name is Jamika Marshall, and I'm very pleased to serve as the Shadow the Scientist coordinator. Shadow the Scientist is an initiative housed under the Creating Equity in STEAM umbrella of programs offered by a team at the University of California, Santa Cruz. We'd like to welcome the CENTA community of teachers and students to this special session. I'd like to now invite Anju Nair to share a few remarks. Anju.
Yeah, hi, thanks, Jamika. So, hi, everybody, welcome to this second session. This is the second session we have on dedicated STS session as a part of TPO Prize 2022. Like last time, we couldn't conduct the session because of north high winds. So, we and Jamika had exchanged a couple of mails and then we had come to a date possibly, and it's working today. And it's happening today, yeah. Thank you so much. Thank you so much. And yes, and may I know that how many teachers have joined as a part of TPO? I can see Richa, Shalom, and then Ekta, right?
So teachers, if you could please raise your
Please
virtual
raise your
hand.
hands. Yes, exactly. Okay, Surbi is there. Yeah, right. Thank you so much. I would, Rahul, if you could add few lines.
Sure. Thank you so much for that, Jamika and Anju. It's an absolute pleasure for us to be part of this session. I'll just give some quick context on why we are here and how we got here. So at CENTA, we strongly believe in creating positive career outlines and guide paths for teachers. We want to make teaching an aspirational profession. Today, we work with 1.5 million teachers across the globe from around 140 countries. And we support them end-to-end in their certification, training, and career growth. So we want to create those paradigms where teachers also feel valued, just like a doctor or a scientist or any other professional would. And to that extent, since 2015, when we started at CENTA, we've been trying to find ways to reward, recognize, and uplift teachers based on their merit. So this year marks the end of the 9th edition of the CENTA International Teaching Professionals Olympiad, which is our annual global competition for teachers, where we test teachers on a variety of aspects from subject expertise, pedagogical content knowledge, and professional competencies. Now, it's an MCQ-based test, so we can't really check for communication very efficiently. So we've kept ourselves limited to this for now, but we evolve, of course, like most other things. Now, as part of this competition, we have a host of wonderful partners across the globe who share this vision of making teaching aspirational and reward and recognize teachers who perform well with out of this world opportunities, quite literally in this case with the University of California, Santa Cruz. It's an absolute privilege for us to be part of this entire session and this guide path that we are on right now to discover more about our own abilities and what lies beyond our worlds. So we're very, very excited to be here. Congratulations to all the teachers. This is extremely well deserved. And a special thank you to the team at the University of California, Santa Cruz. To be honest, I find it a little weird to be sitting here with some of the world's best minds. It's good weird, so that's a good thing. And now I'll hand it over to you guys to take us through the stars.
Thank you for those wonderful remarks. It is a pleasure for me to be here as well. And it is certainly a privilege to work with such stellar hosts like the observing team here and staff of the International Gemini Observatory North. So the International Gemini Observatory consists of twin 8.1 meter diameter optical infrared telescopes located on mountains in Hawaii on Maunakea and Chile's Cerro Pachón, which enables the telescopes to work collectively to access the entire sky. Gemini Observatory utilizes Q-observing mode, in which science staff take observations on behalf of other science teams from all over the world. Staff determine the conditions on the ground and in the air, as well as the scientific priorities, and choose from a pool of scientific programs to observe. Now, in this session, we have the privilege of shadowing the Gemini North observing team, which includes Cicero Liu, Jen Miller, and Sunny Stewart. They will be using the Gemini North telescope, again located near the summit of Mauna Kea on the Big Island of Hawaii, with observations taking place remotely from the control room, which you can see behind me, in the Hilo Base Facility, HBF. So if you see HBF in one of your screens, that is the control room in the Hilo Bay, the Hilo Base Facility right behind me. Now, the instruments available to the observing team during this session include the Gemini Multi-Object Spectrograph, the speckle imager ʻAlopeke, the MAROON-X instrument, which is capable of detecting Earth-like planets in the habitable zone around sun-like stars, as well as the Gemini Near InfraRed Spectrograph, GNIRS. Now, as guides on our journey, we have several who will be with us. That includes Brian Lemo and Emanuele Farina. And we also have a very special guest, Ekta Shah, joining us from the University of California, Davis. Hi, Brian. Hi, Emma. Hi, Ekta.
Hey, Jamaica. How's it going?
Oh, everything is going well. We're excited to get things started. I will turn it over to you, mute my audio and video, and join you over in the room around the corner.
Okay, sounds good. So hi, everybody. My name is Brian Lemo. I'm a scientist, staff scientist here at Gemini North Observatory. To my right is the lovely Emma Farina. He is also a staff scientist at Gemini North. Say hi to the people, Emma.
Hi to the people. Good, good. Oh, been a good night. It was like snowing a couple of days ago, a couple of nights ago.
Even in Hawaii.
Yes, even in Hawaii, on the top of Mauna Kea was snowing. That surprising is not the best condition for observing, but now it seems that we are able to open and to start observing. So fingers crossed.
So Emma and I are actually not observing this evening. The observing team is spotlighted for everybody. That's Jen, Cicero, and Sunny that Jamaica just introduced. We are actually in the same base facility. So we're just down the hall from the observing team, but we're actually not on the summit. This is all done roughly around sea level. And so the telescope is unmanned this evening. And in fact, every night we do not observe from the summit. We observe from our base facility. That helps us think a little bit better since the summit here is about 4,000 meters. And it makes much more convenient for us to get coffee and go home and go to sleep when the observations are over. So Emma and I do observe with the telescope on a fairly regular basis, but tonight we are not doing that. We were doing day duties all day today. So an observatory's work is 24 hours a day. And we were getting one of the instruments, the GNIRS instrument, which was the last one that Jamaica mentioned, ready for tonight's observing, so that we can do the science that we want to do, the community asks us to do. and we were successful in that. So our full instrumentation suite is working tonight. And it turns out, as Emma just said, we have reasonably good conditions tonight. So there's a few clouds, but we're doing pretty good. So I can show really quickly. And then I will pass it over to you, Ekta, to introduce yourself. Let me just share a screen really quick.
That is beautiful.
Okay, so hopefully y'all can see this now. This is cameras. These are live cameras from the top of Maunakea, which is about 30 kilometers away from Hilo, which is where we are currently. These are cameras from the Keck Observatory. So these are twin telescopes just to the northwest of our telescope. These are the two Keck telescopes. Gemini North is sitting right over here. And so actually, I guess we could see it in one of the cameras. Yeah, there we are right there. So Keck is a twin 10-meter telescope, so 10-meter aperture for the primary mirror. We have 8.1 meters, and then there's a telescope over here that looks like a can. This is the Subaru telescope, which is run by the National Japanese organization, astronomical organization. So this is what the sky with super sensitive cameras looks like above Maunakea. So you can see some thin wisps of clouds, but you can also see a lot of stars, maybe some constellations that people recognize, like Orion here.
The Milky Way.
And you can see the Milky Way. So that is where we are observing tonight. This is the telescope that we're using. And I will stop sharing and I will pass it over to you, Ekta, to introduce yourself and where you are.
I'm somewhat far from the telescope, so I'm in California right now. So I am a postdoctoral research scholar at University of California in Davis, and I use lots of observations from many of the telescopes that Brian just showed, along with lots of other observations. And I am a researcher in the group of Brian and Professor Laurie Lubin over here, and our group studies large structures in the early universe. And I am from the state of Gujarat in India. So it is an absolute pleasure to, be here and tell you all about all these different telescopes and observing process and all. And I absolutely admire teachers. Lots of teachers in my life have shaped my career and shaped my journey. So I think, spreading this joy to teachers eventually also spreads the joy to students and lots of people. So thank you so much for being here.
Thank you, Ekta. And I guess you're kind of a grizzled veteran at this point of observing with some of the Maunakea telescopes. So your PhD, you use the Keck 2 telescope quite a bit, right? With the multi-object optical spectrograph there. And you've actually led some of our observations on Keck 1 and Keck 2, and then also on the Subaru telescope. You've kind of been all over the mountain, at least remotely from California.
Yes.
And in fact, you helped me propose for some time for Gemini South for this upcoming semester. So that's even moving further afield down to Cerro Pachón in Chile. If we were to get that time.
Yeah, it's been an absolute pleasure to, observe using all these telescopes that I when I was growing up, I was watching documentaries of those telescopes. So this is like, very surreal. So, and then talking with everybody in India about all this is like next level. So thank you. So ask all the questions in the chat, and, I hope you all take best advantage of this opportunity.
Thank you, Ekta, and thank you so much for joining us, and thank you to everybody for joining us and being interested in exploring the stars with us. So we are taking observations right now, and I'll just share a screen really quickly showing the interior of the dome. So in this picture here, so this is us again. This is Gemini North. We're situated on the east ridge of Maunakea, right next to the Canada, France, Hawaii telescope and the University of Hawaii 88-inch telescope, 2.2 meter, I guess, for most of the world. So for the US, 88-inch, for the rest of the world, 2.2 meter. It's kind of distant from Keck. It's probably, I don't know, 300 meters, 500 meters away from Keck. So can't get a good view here. But if you have a good camera and you're up there during the day and you have good lighting, this is what the telescope looks like. This is tilted on its side to horizon. This is our primary mirror here. And just to give a sense of scale, the diameter of this is 8.1 meters. Our secondary mirror is here. So we have the dome system. Light enters into a shutter, which you can see here from the astronomical target, so star, galaxy, whatever. It comes in, hits the primary mirror, hits the secondary mirror, goes into this tube here, and then there's an instrumentation cage on the back with a third mirror, which we call the science fold, and that redirects the light to one of the instruments that Jamika mentioned earlier. And so just to give a different view of that, this is actually one of Cicero and Jen's observing screens right now. So we're watching them observe. They have, if you can see, so in the, let's see, do I have spotlighted still?
You're spotlighted.
Oh, I'm spotlighted. Okay, so I'm gonna just spotlight the control room again. So if you can see, there's a lot of monitors in there. So we have a couple different roles. Jen and Cicero are what's called the observer tonight. So they're controlling all of the instruments, basically. They're interpreting the plan for the night. So they're assessing conditions. So they're watching for clouds. They're watching for the turbulence of the atmosphere, how much water vapor is in the atmosphere, so on and so forth. And they're assessing which scientific observations can be taken under those conditions, and then configuring the instruments, asking the operator, which is Sunny, who's in the back of the shot there, to move the telescope to a particular location, so that whatever astronomical target that the scientific team that's asking for data can be set up on, and that light can enter the telescope and then enter into the instrument. So there's a lot of screens there. This is one of the 16 screens that Jen, Cicero, and Sunny are using this evening. So a lot of information. You can see even on just a single screen, there's a ton of information here. But I want to direct everybody just to here, if you can see my cursor. So this is basically a schematic. It's just a drawing of a non-static drawing of how the light is interacting with the telescope right now. And so again, so this is our dome structure. This is again, non-static drawing. For our dome structure, this is where our telescope is pointed. So just it's basically a bird's eye view of the dome. This black region here represents the shutter. This is where our telescope is. Here's the science people. And so light comes in here, bounces off this flat green surface here, which is a representation of the primary mirror, bounces to the secondary mirror, and then enters into that tube that I showed earlier, and is then piped to one of our instruments. So there's what we call a deployable tertiary mirror, which can come in and cut the light. So basically, it's just a mirror that moves into the beam of light, and it can redirect it to, for example, the GNIRS instrument or the GMOS instrument. This instrument that we're using now is called MAROON-X, which is one of the ones that Jamika shared. And this is an instrument that's actually sitting under our telescope structure. So it's actually a level down from our telescope, and there's a fiber that's basically plugged into this port, and then it ports the light down into MAROON-X. And then MAROON-X is a very high resolution spectrograph, which is used to look at planets, measure the wobble of stars as planets go around, to measure the composition of atmospheres of planets.
Show the instrument.
And Emma has an awesome picture to show you, so I will stop sharing.
So that's just to give you an idea of the size of these things. That's always impressive. You think they are big, but the instruments are much, much bigger than you think. So the typical size of an instrument is more or less the size of a person, so it's pretty impressive. So you see here, this is the fiber that Brian was talking about, and it goes down, 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 and then it goes down to the ground and go to the actual instrument that in this case is not attached to the telescope as these two. That this is GMOS.
Yeah, thanks. Yeah.
And this is GNIRS on the other side.
Yep.
And so that's the peculiarity, because you need super precise, the instrument needs to stay super stable and never moves. And so the solution, instead of being attached to the telescope, that despite being an awesome instrument that then takes the smoothest movement around the sky you can imagine, you still have some vibration, some rotation, something like that. And so you just put this fiber optic that is super high throughput so that you don't lose any light, and then go down to the instrument that can sit on a basement that will never ever move unless there is an earthquake. I mean, sometimes there are earthquakes, so that's a condition you have to take into account. But most of the time, the instrument is so precise that you can measure velocity dispersion or the position of some line from astronomical object with a precision that is just mind-blowing, better than like a meter per second, or I don't know how to convert what is a meter per second in kilometers per hour.
Oh, I don't know.
I mean, really, really precise. Let's put that way.
Yeah. So you're talking about the velocity resolution of MAROON-X. Yeah. So yeah, a meter per second is very slow on astronomical terms. Yeah.
I've dropped a link to the MAROON-X instrument in the chat in case you want to point out a few important parts on there. And we can come back to it later if you'd like.
Oh, there is two. You can think of this. We have one. Every single instrument has his own daddy or mommy.
I think actually what we can do is so the link that Jamika posted is our official like kind of science for people that are proposing to use the instrument. It gives you a fairly good idea of how you might use it scientifically. It's for proposing teams to understand how they might do science that they envision. But I think what might be interesting to people is to actually see the observations that we're currently taking. So let me see if I can bring those up. Okay, so here is the screen that we use to control the instrument, the MAROON-X instrument. So each one of the instruments has their own controls. So going back to the diagram earlier, we have the light coming in from, in this case, a star. It bounces off of our primary, hits our secondary, goes into our instrument cage, and then goes into the MAROON-X fiber. But once you send that light into an instrument, just like there's all sorts of things you can configure for the telescope, there's all sorts of mechanisms that you need to set up to get the appropriate observations with your instrument. And so some instruments like MAROON-X have very few mechanisms that you change around. And the idea being for MAROON-X that there's a certain type of science that people would say, aha, I have an idea and I need super high resolution, spectral resolution. And so I am going to propose for the MAROON-X instrument because it by default has that capability. So a certain type of science can use this instrument. And so I'm actually not that familiar with this instrument because this is not the science that I do. This is exoplanet science, so planets outside of our solar system. The types of observations that I normally take and that Emma normally takes are much lower resolution. We look at galaxies that are very, very distant. But if you needed very precise spectral information on a source, which you do when you're looking at a planet's atmosphere, or you're looking at small movements of a host star that has a planetary body or many planetary bodies around it, then you would use this type of instrument. So this type of instrument is called a spectrograph. And what happens with the light when it enters into the fiber and then enters into the instrument is there's multiple dispersive elements. So a prism, effectively making a rainbow. And these are very, very complicated and expensive prisms. So they can break up the light very, very finely. So not just like into, blue, green, yellow, red, but really like blue and just slightly more red away from blue. And so this covers what we astronomers call the optical range. So this is roughly what the human eye can see. It goes from about 450 nanometers, something like that, to about 900 nanometers. And it has two channels, we call channels, that are the light's split by a dichroic, which basically is splitting the light into two. And the bluer light, we've helpfully colored blue here. And then the redder light that we've helpfully colored red here. So this is so at 3 in the morning when you're very tired, you remember which one is which, just by color association. But
not always.
Not always. But this is not actually the color of the light that is coming out. These orders here, so these kind of horizontal strips, this is emission from the star and from the atmosphere, the Earth's atmosphere, and everything in between, as well as potentially the planet that's being looked at different wavelengths. So different wavelengths of light are represented here as different X locations in this charge coupled device. And so this is the red side, this is the blue side, and these horizontal yellow things that are in both of these CCDs, charge coupled devices, is our laser, what's called laser frequency comb. And this is a very precise calibrator that tells us when you take a dispersed image, so when you have the light from the star and the Earth and everything, and that light is registered on your charge coupled device, you can say, aha, this location right here is precisely such and such wavelength. So that I know to better than 1 meter per second, the location of basically the velocity location of this light versus this light versus this light. And so you can measure very small shifts as you're observing a particular star. So if you're looking at a star and a planet's going around and the Earth is here, there's going to be a gravitational wobble that's induced in the star. It's going to move side to side. It's going to move forward and backward. The forward and backward movement is what we can measure. So along the line of sight is what we call it. That we can measure because it induces a Doppler shift. So there's a change in the wavelength of light that that we see based off of whether that host star is moving forward or moving backwards. And so by measuring that velocity shift, that movement, you can, and understanding something about the properties of the host star, you can understand something about the interaction between the planet and the star, first of all, and then something about the properties of the planet itself. So right now we're actually doing a transit observation, I think. And so this is I think it's honestly one of the longest observations we ever do with Gemini. So we're on a queue system, which means we usually kind of move around during the night. Where you know, people can say, "Ooh, I just saw something explode in the sky, and I want to go look at that." Or you know, we're trying to balance all of this scientific programs in a given night. And it's pretty typical that we spend, depending on the instrument that we're using, spend maybe half an hour, 45 minutes, an hour, hour 15 on a target, and then we move to another target because it's more optimal to move to that target, so to a different astronomical object. In this case, this is a time-sensitive observation, so we're following over a Jen Cicero, is it 3 hours, 3.5 hours, something like that?
Yeah, it's 3.5 hours.
3.5 hours, okay. So 3.5 hours, we're sitting just integrating on this star. And so you can see here, so this screen right here, Jen and Cicero set up, and it dictates the number of exposures that we're going to be taking. So the number of pictures basically that we're going to be taking, how long the exposure time is for the red side and the blue side. So roughly about 5 minutes. And so 5-minute exposures, 31 of these exposures. And so I'm guessing the proposing team is really interested in seeing how the data change as a function of time. So as the planet, I guess, moves in front of the star, is my guess is what's happening. As the planet moves in front of the star, there's going to be changes in what we see in terms of the elemental lines that are emitted in the spectra here. And so,
yeah, Brian, we're actually transiting right about now for this target. Yeah.
Woohoo! Yay! Would you guys mind bringing up in the MAROON-X screens like a DS9 of like one of the images that come out?
Yeah, so do you want to see what the raw data looks like?
Yeah, that would be awesome. Yeah.
So yeah. So this one is the last one? Okay. Yeah, we can do the last one. Sure. Okay.
Yeah, so this is the red camera, right?
Yeah, this is the red camera. Big enough. Into
And so what people are seeing here is just a bunch of different, so emission from a bunch of different wavelengths of light. And so I guess wavelength increases, if I remember correctly, so from left to right, and then from top to bottom.
and this is the backlight laser, and this is the data here.
I don't know if we can see your cursor.
Oh, okay. Well, you know what it is. So I don't know. Yeah.
Yeah.
I don't think it works for me. Yeah.
But yeah, so these are so these dark bands here are probably I'm not sure. Is this inverted? I'm not sure what the scale is, but I mean there's probably absorption from our own atmosphere, there's emission from our own atmosphere, and then probably many of these lines are associated with the photosphere of the star, of the host star. And then I guess in this case, they're maybe attempting to see additional absorption from elemental lines in the planet's atmosphere. And so we can understand something about the composition of that planet and the interrelationship between that planet and the host star. So I think in this program, they're looking at a M dwarf. Is that right? So they're looking at a star that's probably half as cool as our sun and maybe roughly half as massive. And these are good places to look for, well, a lot of things. They're lower mass, so planets don't have to be as massive to induce movement in these stars. They are not super bright, so planets can be fairly close and be what's in a region called the circumstellar habitable zone, so a place where liquid water can exist. They do have quite a bit of odd radiation that's coming out of them, and so some people think it may be inhospitable to life as we know it, but it may also be a good place to look for life because of for example, the contrast between the star and a planet. It may be easier to do direct imaging. It may be easier to measure atmospheres. So that I think in this particular program, they're looking for the relationship between the thermal properties of the star, like convective properties or something. Did you happen to check it out?
I check it out, but this is not my science. It's impressive what they're doing, but it's hard to interpret.
But yeah, I mean, they're basically looking at, they think, I mean, so stars and planets form together, and there's an interrelationship in the forming system between the protostar and the protoplanetary disk. And this is really Cicero's wheelhouse. So I might just, Cicero, if I say anything stupid, please, please correct me. But there's an interrelationship between the star forming and the protoplanetary disk. And there's going to be interactions when these things form, and then as the life cycle continues, the properties that, for example, the convective properties of the star may change how the planets form over time. And so the amount of radiation that's being output, the type of radiation that's being output, can disassociate material in the disk. It can exert radiation pressure on the disk, and can change the spectrum of the basically the mass of the planets that are formed and the location of the planets that are formed. So that's probably exhausts my knowledge on that. I don't know if Cicero, if there's any fun planet stuff that you want to share.
I think you covered it up. You covered it pretty much.
Did I? I'm surprised about that.
Yeah, Jen and I were trying to show another epoch of data as the data are rolling in.
Okay.
It looks very similar to the last one.
No, but you see the planet.
Ooh, there it is.
Yeah, that's the
pretty
point.
much.
These are what we call raw data. That means these are the data that just come out from the telescope, but there is a lot of processing that goes before actually being able to do science. So in this data, you can see everything that, as Brian mentioned, there is not only the astronomical light, that is the one we want to highlight, but there are all the atmosphere emission, every thermal component that is caused by the instrument itself, despite trying to be shielded, everything is, there is always something happening. And there are all that, despite the detector, the part that is actually collecting the light is trying to be as precise as possible. There are some features, there are scratches, and there's what is called cosmic rays. It's actually something that is really annoying. So in the entire universe, or close to our Earth, to the Earth, there are actually particles that are charged and they move really, really fast. And they can cross everyone with no problem. Every day you're crossed by hundreds and thousands of cosmic rays and you don't care, and you never ever notice. But when you try to do super precise measurement, these things are really annoying. And Brian was pointing to one of these. So you see that there is a line crossing one of the spectra, and these things actually contaminates what we want to do. And so the things you do, you are, given that they have a super specific shape, you see that you can spot by eye. They are basically straight line or clearly extremely bright points around. And so we can either try to identify them or remove it, or say that these objects are really, really, really fast. And so if in average, this thing will not appear in the data, it means that this is a fake contribution. So after we remove all of these things, what we are left is that pure astronomical signal that needs to be calibrated in some way. So that's why we have the lamp associated. So that's allow us to have a precise measurement of where every single line is in the rainbow. And it's really, really precise. You have to imagine that this entire figure is roughly 1,000 pixels wide, and every single line you see is a part of the rainbow. So you have, I don't know how many, you have several hundreds channels, of which every single channel is divided in thousands of pixels, and that's how precise you have your measurement, more or less. There is additional things there, but it's just to give you an idea of how precisely are we trying to dissect the rainbow in this data. I think I'm out of the things I know about this.
Yeah, so as we mentioned in the registration for this session, we have no idea what we're going to be observing on a given night at Gemini North. So it completely depends on the conditions. It depends on the programs that have been observed on a previous night. Depends on the instruments that are available to us. If, for example, heaven forbid, something happens to GNIRS during the day, and we can't fix it, then we no longer have the ability to observe with that instrument. And so tonight, it so happens that there was this planetary transit, that our conditions were good enough to observe with it. And so we are sitting on this observation, which is seems really cool, but nothing that Emma and I know anything about.
And actually, this is the type of observation that we prefer, because aside of monitoring and be sure that nothing's happening around you, more or less you can relax and you have time to go to take a leak in case you need to pee, and like drink a coffee or do this kind of normal situation. But there are other instruments that are way, way, way more demanding, and in really extremely scientifically useful and amazing nights, but extremely stressful. You may be in front of the computer and actively doing things every 20 minutes of an hour. And it's basically, if you do that for 10 hours in a row during the night, I swear in the morning you're destroyed, and you really, 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 really want to go to bed and crash. So this is a great type of observation, because you just stare to the same target for hours and hours, and you're extremely happy with this.
Actually, Jen or Cicero, do you mind bringing up the main MAROON-X GUI so we could show part of the reason why we can relax? Yeah, so this is one of the super amazing things about the MAROON-X instrument. So on the sky, when we're taking an observation, we have what's called a guide star. And so we have, in this case, we have a peripheral wavefront sensor. So just a secondary mechanism that is tracking the sky as the Earth moves. But MAROON-X has this very tiny fiber. We need to be very precise to get as much light as possible. So that's this circle, this green circle that Emma's highlighting right now with the mouse. And sitting in the center of that green circle is this host star that we're measuring the transit of. And you can see it, the star bouncing around a little bit. So it's bouncing around due to maybe our tracking isn't super, super, super precise to the level of, 10% of this fiber width. It could be that the atmosphere is jumping around. So basically the turbulence of the atmosphere is causing the apparent position of the star to move. But there's this internal mechanism in MAROON-X that has a couple of measurements up here. So this is T/T axis 1 and T/T axis 2. This is actually an internal mirror, so it's it's a fourth mirror. I mean, we have our tertiary out of the way, but it's a fourth mirror, and this is actually embedded inside of MAROON-X, and it's following the star, the light of the star, the apparent location of the star, throughout the observation. And so if the star starts to jump, the MAROON-X instrument recognizes that it's moving, or apparently moving, and it moves this internal mirror on one of two axes. So it's tip and tilt. That's what the TT stands for. So tip, tilt, and you see these measurements here. And over time, these will probably increase. So there's something called atmospheric dispersion. So the atmosphere changes the apparent location of the star over time, and especially if you're following a target for a very long period of time, this can cause an apparent shift. Another cool thing about MAROON-X is it has an atmospheric dispersion corrector. That's what this ADC thing is over here, which is a prism, I guess. And it basically, because blue light and red light are dispersed differently by the atmosphere, so just like a prism making a rainbow, the apparent location of the blue and the red light changes as a function of where you're looking on the sky. And so this prism corrects for that over time. But there's still other movement that can occur. And so this tip tilt mirror will do some work over the course of this observation to make sure that all the precious light that's coming from the star enters into, as much as we possibly can, enters into the fiber and is used to then be dispersed and to measure the scientific measurements that the proposing team wants to do. So there's even moving past the telescope into the instrument, there's tons of complexity inside an individual instrument. And keep in mind, this is one of the 5 instruments roughly that we currently have available to us.
And the 3 little points here are actually not stars, but these are our laser that we use to calibrate the spectrum. So to be sure that everything that we are looking is perfectly consistent with each other, we don't want to have like lights, like, this is the way you can measure precisely the wavelength or the color of every single pixel. And instead of having it like on separate or like try to do something more complex, you just try to reduce the possibility that things can go wrong. And so you observe them basically around your star. And so you are sure that interpolating between the 3, you will have exactly the information on the wavelength as precise as possible. And that allows you to reduce every single systematic, every single issue that you can have by trying to do this kind of measurements. And this is unique for this kind of science because that is required for this kind of science to have this precise measurement on the wavelength calibration.
I think we should open up to questions if people are interested in asking questions, if students are interested in asking questions. I know we've thrown a lot of information at people. So if there's anything that we can answer, either in the chat or if you want to raise your hand or however you want to do it, we very much welcome questions.
Yes, I've been inviting people to post their comments and questions in the chat, but yes, if you'd like to raise your hand and be unmuted to ask a question, teachers or from your students, we are happy to do that as well. And that can be anytime throughout the session. You all have been sending me some direct messages, which is great. But yes, just raise your hand if you'd like to ask a question or share something.
Yeah, please do, because probably a lot of what we're saying is it seems like a lot, and from the other side of the world, it's hard to get grounded and like what we're actually doing, what these observations are. So we're happy to answer any questions at any level. Maybe since things are going really awesome with the observations. So yeah, the MAROON-X is doing its job. It looks like, let's check the weather. So I'm being a little bit lazy here. If I were observing, I would be like nonstop checking the weather, making sure that things look good. But it does look like conditions are still very good. The clouds are, almost non-existent at this point. And let's see if we can bring up something else. Let's bring up. Actually, you know what we could do? We can do. Where is it? 0. Ooh, bad timing here. So this is another one of the observing screens that Jen and Cicero are using. This is what we call strip tools. And so we have a very large number of sensors and measurements that we take during the night and during the day to assess conditions. And this is extremely important because when a proposing team sends their idea to the Gemini telescope, they have very specific constraints for the conditions for their science. And so if we were to take observations in cloudier conditions than people request, or with a more turbulent atmosphere than people request, or with a higher amount of water vapor than people request, it could actually be that we're not taking observations that are scientific quality for the proposing team. And so they let us know this is the range of conditions that we can accept. And one of the many jobs of the observer, which is Jen and Cicero this evening, one of their many jobs is to monitor a large number of sensors and determine, okay, we're good to continue with this observation. It seems like we're in a good position to get science quality data, or no, conditions have changed quite a bit and we have to then shift our observations to another program. And we always have, one of the really awesome things about Gemini is that we always have a queue of observations ready. So if even when the conditions are really bad and we can only see, a few stars in the sky, there's still an observation that we can take. This is opposed to another type of observing. So this is called Q observing. Another type of observing called classical observing, which is where a given set of scientists with a given scientific goal go to the telescope, or virtually go to the telescope, control the telescope from somewhere in the world, and they have a scientific program for a given night. And it doesn't matter really what the conditions are, that's the night they're given. And so, like, for example, myself and to a lesser extent Emma look at very, very faint things in the sky. And so if we get to the telescope, it's very hard to get telescope time. You maybe get, if you're lucky, you get 6 nights a year. And you get all excited, you prepare all your observations, you spend countless hours getting ready, and then you get to the telescope and it's cloudy. You don't really know what to do. You always have a backup plan, but that may not be optimal for what you're trying to do.
That's called backup for a reason.
Yeah, so it's backup in that you are completely disheartened when you get to the telescope and you say, okay, what else could we possibly look at that might be interesting? But so there's a lot of virtues in that you could be adaptable, you can be agile with your program. You can, if you find something even 3 hours earlier, you can say, oh, well, let's look at that. But it maybe is not the most optimal use of telescope time sometimes. So here we always have the optimal program for the conditions. And so we're just so this is real-time monitoring of several of our sensors. These upper two are really important. This measures the astigmatism that we're seeing in the observations with our wavefront sensor, and then the what's called seeing, so basically the blurring of the atmosphere. And it looks like actually this is P2, so this is peripheral wavefront sensor 2, which is reading a value of 0.4. This is in a unit called arc seconds, which is 1/3600th of a degree. So very, very small. A degree on the sky is a fingernail at arm's length. So it's 1/3600th of that. And so it's half of that. So 1/7200th of that. And so very, very small angular area that what we call a point source, like a star. Stars are big, but they're very, very far away. And so they basically look like points in the sky. And so the atmosphere spreads out the light to this value here. That's what we measure at the telescope. And so the size of the MAROON-X fiber is 0.74 arc seconds. And so measuring about a 0.4 arc second seeing, we're basically getting all of the light from the star in the fiber, which is great. And this is apparently what the proposing team asked for. They said it does actually look like a fairly faint star for MAROON-X. And so they're trying to get every single photon they possibly can into the fiber.
That's actually to give you an idea, in typical places, the level of this number, this called seeing, is roughly double than that. So if you go on a random night, you will expect this value to be around 0.8. And now we have 0.4. That is actually like incredible. And that's the reason why we are all here in Hawaii. Aside of like being an amazing places with all the beaches and everything, the main reason that the Maunakea, that is the mountain where all the telescopes are, is actually have two characteristics that are pretty incredible. This one is that is 4,200 meters. So it's really, really, really tall. And starting from sea level is one of the tallest mountains not from sea level, from the bottom of the ocean is one of the tallest mountains in the world. But even from sea level is pretty impressive. And it is in the middle of the Pacific. That means two things. Being in the middle of the Pacific helps a lot because we are isolated, like we are far away from everything. That also means that there is not that much contamination from lights from like big cities around us. Because Hilo is the biggest city that is on the island and counts 300,000 people. So it's sort of a big village more than a city. And the other thing is that given that we are in the middle of the Pacific, what we call when the wind arrives, it doesn't have any turbulence in it. And that brings us this number to be extremely small. And that's what basically why we are here. And you can see this way. It is not exactly correct. But if this number goes down a factor of 2, it's like having a telescope that is twice as big to collect photons. So being here a factor of 2 here with a telescope that is 8 meters in diameter is like having a telescope that is 4 meters in diameter in a normal place. That's the opposite.
16 meters.
16 meter diameters in a normal place.
Yeah.
And that's why we are all excited to be here and we are all happy to be here.
Yeah.
And this night is confirming it that way.
Yeah, no, this is really, really good. This is exceptional conditions. P2 measuring under 0.4 is fairly uncommon.
Yes.
And people probably will have an opportunity at some point to engage with a session with the Lick Observatory, which is on Mount Hamilton, just outside of San Jose in California. And just to give an idea, typical night at Lick, the seeing is in between 1.2 and 1.5 arc seconds. And so to Emma's point, if you double it, you have to double the primary mirror aperture roughly. This is 3 times or 4 times the amount. And so you have to build a very, very big telescope to make up for that. Also, there's a lot, so San Jose is not an isolated place in the middle of the Pacific. There's a lot more than 30,000 people that live in San Jose. So there's a lot of light output, especially by sodium lights that cause the sky to be very bright. And so that can cause issues with astronomical observations. There's also water vapor. So we have not a lot of water vapor here in Maunakea, also in Cerro Pachón, but other large astronomical observatories have to deal with water vapor. So for example, in the Canary Islands, that's a place where they have to deal with a considerable amount of water vapor.
And the other incredible things that actually the mountain is so tall that is above what is called the inversion layer. So if you ever take a plane, when you when it's cloudy where you are taking off, and then with the plane you cross the clouds, and the clouds look like they are flat below you. That's actually Maunakea most of the time is above that layer. So Hilo is one of the wettest places in the world. So basically every day it rains here, and like we are in a sort of a jungle condition, but we can have like pouring rain outside our windows and still observing the most amazing sky in the world. That's kind of unique. And the number of nights that is good weather, aside like a couple of days ago when it was actually snowing, but that's an exception. Most of the night actually they look like this. That's what Brian is showing. There is like some clouds on the horizon, but if you look just above you, there is absolutely nothing. And you can just stare to the stars for hours and hours and hours with absolutely no problems. Is that the moon?
I was gonna ask.
Yeah, I think so. Yep.
Really bright.
Yep. Yeah, we're entering into what we call bright time. So we're moving from darker time to brighter time. So MAROON-X is actually a fairly good instrument, even though it's in the optical. It's a fairly good instrument in bright time because we're generally looking at fairly bright targets as well. And so the brightness of the moon doesn't affect observations as much. But pretty soon, so I think this is waxing. We're probably in waxing gibbous or something like that. And so we'll move over to the near infrared heavy schedule probably in the next 4 or 5 days, because in the near infrared, which is redder than the optical, the moon's light doesn't affect observations as much. So the change in sky brightness when you go to the reddest wavelengths in the infrared. So you start it at red optical, which is just red, like this red. Then you go red, 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 further. So lower and lower energy photons, all the way to the point where the atmosphere basically is no longer transparent to those photons. At that point, which is about, let's say 2.1 microns, so 2100 nanometers. The full moon makes almost no difference. So the change in sky brightness, full moon in, this is called the K band, 2.1 microns, is almost nothing. Whereas if you were looking in the optical in the blue, you would blind the telescope and fry your camera probably. And so it really matters. You have to take into account not only the conditions, the clouds, the water vapor, the turbulence in the atmosphere, but also the moon phase. You also have to take into account timing constraints. So for example, this transit that's occurring right now, this is something that may only happen once per semester, once per year, once per 2 years, once per 3 years. And so it may be that tonight is the night that we have a chance to do it. And so it's a very multi-dimensional space that people that plan the observations and people like Cicero, Jen, and Sunny that execute the observations have to think in order to get the best science from a given amount of time on the telescope.
Another way to see this is that actually the light of the moon, the moon doesn't emit light, it just reflects the light of the sun. So it's basically, when you don't stare at the sun, but when you look around during the day, most of the lights is come out in the optical regime. That is where you see. And the emission of the sun drops a lot in the infrared, as Brian said. So we are, when you observe during the night, you have the moon is basically having a small sun in the terms of like how the emission comes out. And so basically, if this full moon, you try to observe in the green, that is where the peak of the light of the sun come out, you're having like, you're basically blinded. But if you try to go as far away as possible from the green, then you can observe with no problem at all. And Gemini is another peculiarity that not many instruments has. So most of the telescopes that observe from the ground observe what Brian called the K band. That is 2.1 micron, 2,100 nanometers, 2,100 nanometers. But Gemini has been built specifically to go as red as possible. And so we can actually push the study to go even redder than that and go to like 3.4 micron, that is 340 nanometers.
3400.
340, yeah. or even 4 micron, that is
4,000.
4,000 nanometer.
Yeah.
And so actually these are extremely challenging observation. But if you try to observe the brightest stars, so like the most incredible object that are in the sky, you can actually collect this data from here. To make a comparison, they are one of the few other instruments that can make the same type of observation is actually JWST, and is on space.
So it's the James Webb Space Telescope.
Yes.
That's the new-ish telescope that was launched about 2 years.
Yeah. 3 years, 3 years.
Yeah.
So the same type of observation that you can choose, or either to do it here from Maunakea, or you have to go into space. That's a pretty exciting sentence, I would say.
Speaking of which, Cicero, if you have a quiet moment there in the control room, you were actually one of the inaugural users of the M-band capabilities, so this 4,000 nanometer capabilities with the GNIRS instrument, with our new capabilities, what we call the high resolution integral field unit spectrograph. Do you mind telling people, like, just real quickly, like what you were observing and why?
Yeah, absolutely. So it was really exciting last year around mid of December to observe was this mode. So this is a newly commissioned mode that basically takes a picture at every wavelength channel with high resolution spectrographs, and you get a field of view that is kind of rectangular-ish, 1.25 arcsecond by 1.8 arcsecond on the site. So this really allows us to look at some of the closest planetary systems in the universe. So the observation that Brian and I and Emma did, and I think Matthew was also on the observing team that night, was we looked at this famous planetary system called AB Aurigae, which is known to have very beautiful big spiral armed features with the kind of gas and dust around it. And so our goal is to try to see if there are any kind of planet forming regions that has a gas. So basically how planets form is that you form a core for these giant planets from metals. So as astronomers, we call everything that's heavier than hydrogen and helium in atom metal. So these things forms the very interior of giant planets, like, for example, our Jupiters or the giant planets in our solar system. So the same thing goes for perhaps things elsewhere. And so that leads us to this web page that Brian's showing on the screen called AB Aurigae. So it's a really young and close by system. So our sun is about 4.6 billion years old. This planetary system is only about maybe 1/1,000,000th of that age. So this is only like, say, 10 million years old since their star has been born. So there's still a lot of gas and materials around in that protoplanetary disk. And those these are expected to be sites that's actually forming planets. And so previously, shorter wavelength coverage in K-band and a lot of people using Subaru has seen really amazing features that's spatially resolved with this disk. And so we tried to use that capability, but no one have ever done this in the M-band before. So this was actually the first time of this kind of image has been taken. So these are lights actually generated from the thermal emission, which is if you have like one of those night vision goggles and you take a look at your cat or your dog or something else, you'll see them glow in the dark. So this is the same type of nature that in this planetary system. So you can see that on the top is the overall, how it looks like the center is where the star is, and that's the hottest part, and so that glows the brightest. And as you move towards the outer rim of this planetary system, it gets colder, and so you can see that the light thins out a bit. And then on the bottom are 3 images of these, so we call it spectral differential imaging. So basically, these are pictures of where the carbon monoxide gas is in the system. So these are gas emitting at different temperature, and basically the carbon monoxide atom is basically one atom of carbon and the other atom is oxygen, they would rotate in space and also have bending and stretching motions. And these motions allow us to really take a look at them at these really long wavelengths in the near infrared. And so by using this kind of study, potentially, when this mode gets to used, people would have capabilities of understanding what are precise sites of planet forming in action. And so that's why I was really excited and very honored to be helping Brian and Emma and the whole GNIRS team to do some of that commissioning work. Yeah, sorry, that was kind of a long explanation to your short question, but
no, that was perfect.
Really excited.
I wonder, Cicero, just a naive question. How do you know that these emission features are coming from carbon monoxide? So I guess you just see emission from at a certain wavelength, and then you ascribe that to carbon monoxide. But how do you know that?
Yeah, that's a great question. So we look at a series of lines. So actually, this observation goes from around 4.8 microns all the way to 5 microns, which gave us about 1,000 slices of this kind of images. And you don't only rely on one slice information, you actually look at all the features simultaneously. So we know that in a laboratory experiment, if we put carbon monoxide in a shock tube and we heat it up and we shine lasers through it and let them glow, that would produce a series of spectrum that you can plot out as a function of wavelengths. And so long answer short is that you look at the joint relationship of different lines emitting throughout this region. And we see a forest actually in the emission pattern. So that gives us pretty good confidence that these lines are carbon monoxide low vibrational emission instead of other species. And there has been, I guess, non-spatially resolved long slit observation of this target, also showing there are a lot of carbon monoxide that is in this planetary system. But it's really amazing that we can actually see this in this kind of picture, like in the in IFU sense. I don't know if that's convincing. It could be something else, but from our knowledge of laboratory databases, that's the most likely species, chemical species that we have.
Yeah, and I guess
sorry, go ahead.
Yeah, you have 3 different lines here, so you're kind of looking for once you have one line, then you're looking for the energy levels of these different transitions or rotations.
Yeah.
And so you understand, okay, if I see a CO line here that I ascribe to a certain energy, then I expect to see something else at a different energy, and lo and behold, you find it. And then you say, I expect to see something at a different energy, also from CO, but from a different rotational state or vibrational state. And lo and behold, you find that. And the fact that you find, 3 of these at the precise location that you expect based on laboratory experiments, that tells you, okay, that's definitely that. We can ascribe it to that molecule rather than to, say, hydrogen or something else.
Yeah, that's right. I think you gave a really good summary of what that is. Yeah, I think there are potentially more lines in the data. These are 3 examples that we are showing that are brightest. But there are also certainly other lines that can be ascribed to basically CO emission in this data. So, yeah.
Thanks, Cicero. I think that Emma's going to share a low resolution IFU image. So this is our other one of our other capabilities on the GNIRS instrument. And this is a little bit lower spatial resolution, a little bit lower spectral resolution, but that doesn't mean it's not super, super cool in its own right. Mm-hmm. So what are we looking at?
So this is actually the rainbow you see in the middle. They're actually the real data. So our in-house space artist is Jen, that is here, take care of this image. We are really happy that she is here because she makes like super awesome imaging. Like you can look at this, this is awesome. So that's exciting. But what we could actually look at this, you see on the back is actually a normal image that you take on the sky. This is what decades of 4 decades astronomers did. You look to the sky, you take your big telescope, you point to that, and you have an image of what you're seeing, and then it's look, but you lose a lot of information. So these are 2 galaxies that are interacting with each other, maybe 3, but most likely 2. And then when you try to zoom in the center, and then you take this new instrument that is called an integral field spectrograph that actually doesn't give you only the information, the spatial information, but give you at the same time both spectral and spatial information. You can try to dissect what's happening in the real center. And if you squint your eyes, you may notice that actually there are not a single object there, but actually 2 of them. And so what is showing the bottom, what Brian is pointing at, is actually the 2 different supermassive black holes that are actually black holes that are of the order of 1 million or even 10 millions or even 100 million times more massive than our sun, that are usually located in the center of the galaxies, that are in a process of moving close to each other together, and most likely in the future will like collapse to each other and become a single object. But now when you look to the image in the back, you actually cannot really see that. But when you take these objects that are these new instruments that give you this information with higher spectral spatial resolution, you see the 2 components, one or the other. And as Cicero was mentioning, what we really like is that when you see emission line coming from an object, that means that there are some elements, chemical elements that happen to be around this object. They're highly excited, and so they emit more light than we do in the normal conditions. And so these became super bright. And every single one of these colors that you see is targeted to a specific emission line of the hydrogen. So that's a like different type of emission that comes from the hydrogen. And you see that when you start to compare the these different lines, you start to say, okay, this not like, you do that more quantitatively, but in a first order, you say, oh, I see there are differences between the different lines. I see that there is like a bridge that connects the left blob to the right blob. And so I'm learning something about that. It means that there is hydrogen between the 2 objects, and not only the 2 objects are fully separated from each other. And that's actually what we are doing. Like, this is super exciting to collect data, and we spend a lot of time in the control room. We spend a lot of time to make sure that all the instruments work. But at the end of the day, what we want to know is what are the physical reasons, how we can transform this data with this information into something that has like physical meaning, a scientific relevance, or some kind of some of these informations. I think both Brian and I are super excited by these 2 instruments because they are basically the newest addition to the suite of instruments that are offered by Gemini, and we spend a lot of time to try to make them available for the community, and they are started to be used since last year for the first time. And so these are our babies somehow. They sometimes are cranky as babies. Most of the time are cranky, but
Labor of love.
yes.
Yeah. Well, thank you, Cicero. Thank you, Emma, for showcasing the new capabilities and all the cool science some of the cool science that we can get out of it. And yeah, I guess potentially we'll be doing some GNIRS observations later this evening after the transit finishes. I wanted to invite ALTAIR to maybe give a small talk about the science. So zooming out from so I think we started with AB Auriga, which is very
we started with a planet passing in front of another star.
Okay, yep.
Observed from another
planet.
planet.
Okay, yeah, that's true. Okay, and then we went to the
that is still happening.
Which is still happening, yeah.
We're not getting
We
the
promise.
answer, it's still happening.
Then to AB Auriga, protoplanetary disk, then to a reasonably close by galaxy that has a couple of merging black holes, and now we're going to zoom out to the very distant edges of the universe with ALTAIR.
Yeah. I just want to say, like, because we observe galaxies that are very, very far away, as I will describe. So it is actually really fun to also see this kind of relatively nearby systems. And in a way, it is incredible that, if you kind of imagine that we are getting observed probably somewhere, there is some possibility. So it's kind of like, you have Earth passing in front of sun, and then somewhere somebody has like good eyes or telescope is observing, and then trying to understand something about Earth's atmosphere through these observations. And sometimes, so I don't study exoplanets, but I think there are some lines that people consider to be more coming from, not natural processes in a planet, but more like, human-like activities or some other things. So, so I think some people also use like the information that you get about the atmosphere to kind of estimate, like, what is the likelihood that whatever emission you're observing is from natural processes or actually from some system like humans or something. So yeah, super cool stuff.
I did have a quick question before we transition, Ekta. Emma mentioned that last image that we were seeing, Emma, if you could please share that screen again, and that is an image that Jen Miller, who's right here with us in the control room, processed, created. I'm not sure. Jen, could you give us a bit of insight on what you did to this amazing image before we move on to Ekta? Before we move to on to Ekta, please, because I'm very curious. This is an amazing image.
So I'm part of a team, so it wasn't all me, but we took the DECAM data and made this color image with it. So depending on what filter is used, so 3 filters were used in this image, and we were able to make a color image from it. So they're basically all of the images come out as black and white, and we're able to stack each filter, which has a different, basically it's picking out different wavelengths. So we assign the filters as our eyes would see them. So the red is the longer wavelength, and then the green is in the middle, and then the blue is shorter wavelengths. And those represent different chemical elements in the galaxy here, and also the stars. And then what we did is Emma sent us the data from the IFU, and then we were able to make this cube, and then basically make it so that, like I mentioned in the color image, so we made the red is the longer wavelengths all the way to kind of purplish. And then we basically took slices from that cube data. So you can see, so you can see at each wavelength, like for instance, where Emma's has that. So then you can see what that looks like, kind of like 2D instead of from the 3D cube.
It's super pretty.
It's very pretty.
It really is.
It's amazing. I wish I could do that.
Thank you for the explanation, Jen. I was just really curious how you and your team create these amazingly, beautiful but also scientifically useful images. Thank you.
That was fun.
Just give me 1 second. I just remembered to grab something.
Oh, absolutely. Absolutely.
So I think Ekta is going to talk about the science that our group does. And we don't use Gemini that much. We have used Gemini North in the past. We are hoping to use Gemini South in the future. And maybe Ekta will just make a brief mention of that towards the end. But we actually primarily use the Keck telescope, which is the twin telescopes that are on Maunakea, the camera that I showed earlier was from, and the Subaru telescope, which is right next door. And so I think Ekta is going to talk about maybe some of our observations with the Keck telescope, and our pictures are definitely not as pretty as the one that was just shared. So we're looking at very, very distant galaxies that are very, very, very faint. And although we're looking for some of the biggest structures in the universe, they're still pretty small as we see them and very faint. So we can make some pretty pictures, but definitely not rivaling what we just saw.
Yeah, at the end, you just look for little dots in the sky.
Mm-hmm.
But there are a lot of little dots close together. That's when Brian and Edka get excited.
Well, if we find the right one, we say curse. Oh no, that was the wrong dot.
Yeah. Okay.
But I'll just say that it's not that we don't use Gemini North because we don't like it, or Gemini South because we don't like it. But the Keck telescope in particular has instrumentation capability which exceeds that of Gemini North and Gemini South for the particular scientific observations that we were doing to make a broad census of galaxies that are very, very distant. But there are definitely some aspects of the Gemini North, Gemini South instrumentation suite that we can use to further refine those observations. One of the reasons we apply to Gemini South is because it's in the southern hemisphere, and so it sees part of the sky that we don't see up here in the north. And so we have been trying to take observations of a target that is fairly far south from the north. That's not a great idea. So we said, okay, let's go from the south. And it's much, much easier to take observations from down there. And so we're trying to use those capabilities. So Ekta, please take it away.
Okay. Okay. So we're gonna very quickly go from our galaxy to lots of different distant galaxies. So, this is our Milky Way, and then we have seen the nearest galaxy, Andromeda, which covers a huge part of sky. And then we also see lots and lots of galaxies, as Emma mentioned, very tiny dots. Some of them are a little bit bigger dots, but most of them are very tiny dots. And then when we kind of zoom in on those dots, we also see sometimes shapes of those galaxies. So sometimes we have this elliptical galaxies or like spiral galaxies. And sometimes we also see this kind of galaxies that are, almost interacting with each other. Other times we also see groups of galaxies. So you might have seen this picture that was taken using JWST. And so you can clearly see there are like 4, maybe 5 galaxies together. And some other times we also see this kind of galaxy clusters that has lots and lots of galaxies together. So these are large massive structures in the universe, and sometimes they have hundreds or even thousands of galaxies. All of those galaxies, the impact of this kind of very large structure on the galaxies that are inside can be very large. It's almost like how our collaborator calls, like, these are like cities of galaxies, right? So if you grew up in a city, you will be very different in certain aspect compared to somebody who has grown up in a farm or something, right? So similarly, the properties of galaxies that are in this dense, large structures can be very different compared to isolated galaxies. So we call these structures galaxy clusters. And what our group studies is actually even the formation. So when these clusters are in the very early stage of formation and evolution, that's what we study. So how did this kind of early clusters look in the very distant universe? So just to give you idea how these things form. Some reason this isn't playing, but so basically as the universe, starts and evolves, you have lots and lots of gas coming together. So the galaxies kind of, because the very dense potential, galaxies come near the center of the cluster and go around it. So which results in more galaxies coming and this region becoming more and more dense. So over time, the galaxies themselves are growing, and this structure itself is also growing. And throughout this time, the gas component, the speed of the gas, the temperature of the gas inside this large structure can vary a lot. And similarly, the star formation rate in the galaxies themselves can also vary a lot. And lots of other properties of galaxies, like their shape, their black hole activity, can also vary throughout this time. So there are lots of things that we can study using this kind of clusters in the early universe. And some of these motivations are also that when we look in the local universe, so in the nearby universe, there are lots and lots of massive galaxies. But these massive galaxies don't form lots of stars. So which means that they must have formed their stars very rapidly in the early universe. So that's one of the questions that we are trying to understand. And to study that, we have to actually identify these kind of systems in the early universe, right? And then see how their dense environment affect the properties of their galaxies. So just to give you idea, these are some of these kind of structures. So you can see that while in the local universe, this structure can look very kind of spherical and very well structured. But when they are in the process of formation, they can look this kind of, their shapes don't look as well structured because they're still in the formation phase. So they can have like different components kind of coming together. So here you can see like, all these different structures have like very different shapes and density. So the red color show kind of measure of over density. So as I said, they can have like lots and lots of different components that can eventually come together and form this massive cluster that we see today. But
so
how
these structures that you were just showing us, these are observed, I guess, roughly when the universe is about 10 to 20% of its current age, right? So this is very, very
How old is the
baby.
universe, Ryan?
13.7 billion years, give or take, give or take. So this is 1 to 2 billion years after the Big Bang, roughly.
right?
So the very infant universe, and already a lot of mass has formed together, but they're not like the massive clusters that you just showed. They're still in their very much in their formation phase. Just for context.
Yeah. So how do we actually observe them and identify them, right? Because what you have to, in a way, remember, right? Like we just see the sky, right? So you have to actually identify that there are galaxies very far away, but they are still closer together. And to do that, you actually have to measure some properties of those galaxies and then actually see whether they are together or not. Because when I just look in some area of sky, there will be like, for example, this one, right? So you can see that there are some galaxies that are bigger, some galaxies that are smaller. So and when you measure the properties of these galaxies, you will see that some are kind of closer to us, some are a little bit far away, some are a little bit more far away, right? So you have to identify like a group of galaxies that is together. So to do that, you have to actually identify these kind of properties of lots of galaxies and then see which of them are together. And to do that, that's why we need this very, very big telescopes, because the galaxies that we are observing, as Brian mentioned, are at very early stage of the universe. So they tend to be very, very faint. And so we want to collect lots and lots of light. And that's why we use like this big telescope. So this is a mirror of Keck telescope, one of the Keck telescopes. And as you can see, it's very, very large. And so there are 2 Keck telescopes. And what we do is like, it's like you have big bucket and then you collect all the light and add it all together to then measure the properties of those galaxies. So let's
I'll just can you go back to that picture, Ekta?
Yeah.
I'll just jump in for a second. No, actually, I think the previous one's slide 17. Yeah, so if people look on the right-hand side, so that's the telescope structure, and it looks a lot like the Gemini telescope, but it has this segmented mirror structure, so these hexagonal segments in the mirror. So but size of the primary mirror is roughly 20% larger. So it collects roughly 40% more light, something like that. But the basic structure of the telescope is very similar. So you see the primary mirror down at the right-hand side of the photo, and then there's a secondary mirror right in the foreground, and then that light is piped down into the circular tube that's protruding from the primary mirror. But one of the differences, and this is part of the reason why we use the Keck telescopes, like Ekta and I use it, and other research groups, is because they have something called a Nasmyth deck, which is you can see in the background kind of, there's a kind of red thing there. And it's like up in the kind of upper left of the picture. Yeah, there. And there's actually a platform around the dome that houses a lot of the instruments. And so whereas we at Gemini, we're very agile, very quick, we can switch between instruments super quick, just by moving our tertiary mirror like this. A lot of the instrumentation at Keck and at Subaru as well are behemoths. These are like super big instruments. And so we have weight restrictions that we have for our telescope. We can't mount a 17-ton instrument on the back of the telescope because there would be issues with balancing and lots of other things. And so all of our instrumentation is sitting there, but Keck and to a lesser extent, I don't know if Subaru actually has it, but Keck 1 and Keck 2 definitely have it, this Nasmyth deck, and they have these huge instruments like the ones that Hector is going to talk about, that have these like incredible large field of view or large multiplexing, so you can observe many galaxies at once, and that's just not possible on Gemini the way it's built. So we're built for a different type of observing, and that doesn't make us better or worse, it just makes us different. And so this MOSFire instrument that Hector is about to talk about, this is a very large instrument that we could not mount on the back of our telescope.
Unless we cheat, that's what we are doing with MAROON-X. We take a fiber and we put it away.
Yeah.
So that's a way to be agile and big.
Yeah, but fibers have their own issues.
Yeah, so you can see it here. Some of the instruments that Brian was mentioning, and here is a human first skill. So I think like if you just look at the picture of the instruments, it doesn't give that much clear idea of the size. So it's good to have like a comparison, and it gives you idea about like how really big these things are. Yeah, so we use different types, mainly 2 different types of instruments on Keck to measure the properties that I mentioned. And I keep saying properties, so that's basically spectrum of galaxies. And just really basic, we have seen this kind of dispersion of light from like CDs or this kind of system, or even in nature. And so that's the basic idea of using grating. So these are like very tiny slits, and that converts the white light coming from any source into a spectrum. And in this spectrum, depending on what type of galaxy or what type of system you're looking at, you can have different lines, and that line will give you information about the galaxy or whatever system you're looking at. So here is the MOSFire instrument that I mentioned. And so the idea is, as I said, like, so if you have this kind of region in sky, and if you want to measure properties of certain galaxies, you will put slits on some of them. So here is some part of the MOSFire instrument. So basically this rods, they go together and then they generate slit wherever you want. So imagine like if you want to observe like this galaxy, then all the bars over there would kind of, it's like if you want to observe my eye, and then you will have bars closing, and then you can just see my eye, right? So it's kind of like that. So because you have to remember that spectroscopic observations are relatively very, very expensive. So you can take picture of sky and have these many galaxies, but when you want to take spectra, it's very much more expensive. So you can take spectra of like in this case close to.
I'll just jump in. It's just this, when you say the word expensive, it doesn't mean expensive in terms of money. It means expensive in terms of time, right? So I mean, I guess time is money on the telescope because it takes a lot of money to run these telescopes.
Right.
But you're really talking about going from an image where you can see 30,000 galaxies in a single click. That's, a couple 100 seconds on one of these telescopes, to just looking at the light of, let's say, 25 or 30 or 35, if you're lucky with this particular instrument, galaxies at once. So you're going down by a factor of, 1,000 or more in terms of the number of objects that you're looking at. So you're saying, I want to pick out particular objects that are of interest to me, and I want to get a lot more information on those.
Right. Yeah. And then, through this slit, so this slit is basically this part, you will have light coming from the galaxy, and then you will get your spectra. So when we get spectra, so these are different wavebands, but when you actually get spectra, it can look like this. And as you can see, I mentioned lines. So sometimes you see this kind of emission line, and that could be oxygen lines, hydrogen lines, sometimes even nitrogen lines. And that will give you information about the galaxies. So this is one of the screenshot of MOS fire image. So you can also adjust the length of the slits in the MOS fire instrument. So if you have little bit longer object or something, you can have much longer slit compared to some other objects. Another instrument that we use is DMOS. So let me really quickly show the DMOS mask. So this is actual DMOS mask, and so I don't know if you can see tiny slits in it. So yeah, but using DMOS, you can observe 80 to almost even 90, even almost 100-ish galaxies. So so basically, yeah, this goes in, this instruments is mounted, behind the telescope. And then when the light comes, you observe lights from these galaxies, right? So the principle is still the same. Instead of the entire sky, you are observing only certain galaxies, but you will get much more detailed information about those galaxies. And
is there any particular relevance to anything that you've studied for that mask, Ekta?
Yes. So I had actually used this mask to identify galaxies that are closer together. And maybe at the time we were not sure, if there is a large structure, but using these observations, we have identified 6 structures that we just published. So so here are the structures that we have identified, and our team has discovered. And
I think you're not sharing screen unless my
okay. That was my bad. Is it good now?
Yep, it's good. Yep.
Okay. So using these observations and many other observations, so we have discovered 6 very massive structures in early universe, and we also gave them names. So I don't know if you can see it clear enough, but we have given them names that are inspired by the 6 senses. So these are Drishti, Surabhi, Shravan, Sparsh, Ruchi. And for the 6th sense, I have decided a name of Smruti, which literally you might already know. It means memory, but the way I interpret it is it's like ancestral memory or ancestral wisdom that is embedded in your DNA. And, that kind of guides you sometimes, right? That's responsible for your intuition. And I also decided to go with this theme because we are literally part of the universe that tries to observe and understand the universe. And these senses are like our first contact with the universe, right? Through these senses, we experience the universe. So that's why I decided to go with this theme and name these structures. And here you can see actually the 3D shapes of the structure. And again, you can see they are, spanning wide range of shapes, and they have many different components. And each of the structure has total mass of more than 10 to the 14.8 solar mass. So very, very massive systems. They have lots of galaxies in them. And they are great laboratories to actually study.
When you say 10 to the 14, just for context, that's nearly a million billion. If that number helps.
Okay, let's say a crore.
Million billions.
Yeah.
That's a lot of mass.
That's a lot of mass. Yeah.
Yeah.
Times the mass of the sun, which is already 10 to the 30, 1.99 10 to the 30 kilograms.
Yeah.
3 grams.
Great. 33 grams. So 30 kilograms.
I will
Yeah.
not go in how many billions is that.
It's that you already said it. It's 1,000 billion kilograms, and then it's a million billion of those.
Mm-hmm.
It's a lot of kilograms.
Yeah. And they provide actually great laboratory to study some of the motivations that I mentioned before. Like when you have this kind of systems forming in the early universe, how did they impact their galaxies? And so this includes like the star formation, the shapes, the black hole activity, and lots of other things. So there are only a handful of such systems, and this 6 structures add to that, relatively small library of such structures. So yeah, and people have already started using,
Just to give context, so it's not that there are very few of these structures in the universe,
high elements,
but that there are just a few known, and it just shows how challenging these observations are. The part of the sky that we're looking in for these observations and try to search for these types of structures, these have been studied with the world's best telescopes for decades now. And still we're finding new things in the in the deep recesses of the universe in these fields. And these parts of the sky are very, very small compared to the whole sky. So this is only 1/40,000th of the sky that we're studying with these fields, something like that. We're basically looking over 1.5 square degrees, something like that. So yep, just like a wedding ring at arm's length, and this is where we're looking for all of these structures. And so there's nothing, at least that we know about, that's particularly special about these regions of the universe. It's just that a lot of people have decided to take observations with very very good instruments and very good telescopes. And so we're getting a lot of information on these parts of the sky, and we try to extrapolate that information to other parts of the universe under the assumption that what we discover in these regions is roughly the same had we looked in another region of the sky, roughly the same properties. There's nothing special about that. But we look in 3 different regions of the sky to reduce what we call cosmic variance. So basically that there is a little bit of difference between when you look in one part of the sky versus another part of the sky. And so you average over different sight lines so that you can average out some of the noise that you get in your observations just due to the presence of special objects. But we found these types of objects in each of the 3 parts of the sky that we look at. And so it seems that these types of systems are actually quite common in the early universe. They're just very hard to find. And so I know we're getting close to the end, but I just wanted to, well, first of all, thank you very much, Ekta, for sharing. But would you tie maybe into the potential upcoming observations from Gemini South, since I see that you have one of the structure that we were potentially targeting?
Yeah. Just give me 1 second. Yeah. So here, okay. So let me share my screen. Okay, finally it's moving. Okay. So Brian mentioned that we might be observing using Gemini South. So actually this structure that is the farthest one, this one. That is the farthest one called Ruchi. That's the one we are targeting. So, I mean, we have proposed to target. So we are basically saying that while we have discovered that structure, there could be still a lot more number of galaxies in that structure. And for that, we want to measure the properties of lots of galaxies in that region. So all the dots that you see here in the black squares are the ones we will be targeting, and hopefully many of them will be in the region of the protostructure, in the region of the large structure. So yeah, as you can see, like, you know, the red color shows like the overdensity part that we have identified, but measuring this properties of this other galaxies would help us better understand the structure of the structure itself. And yeah, so hopefully if it gets approved, then we will be observing a lot more galaxies in this region and better understand the system.
So yeah, so it's one thing to discover these systems, but then, you know, how many galaxies are in Ruchi currently that we know about?
11. Right
11, right? So it's a very massive system. We suspect that there are quite a few other galaxies embedded within them. And so we may have a kind of biased view of the, you know, the few galaxies that we know there. They may be special in some way. And so we don't want to make suppositions based on just that small number of galaxies. And so the goal in part of these observations is to confirm a large number of galaxies within the system and see what the properties of those galaxies are in the very, very early universe, 1.5 billion years after the Big Bang. So roughly 10% of the universe's age. So that's the goal. And right now, in a couple of weeks, a set of scientists are going to be evaluating these proposals for scientific merit and then determine whether or not the ideas that we have are worthy of time on the telescope. And if they are worthy, then they will award time, and then it will go into our queue system. And then we will observe it in the same way that we're observing scientific observations or scientific programs this evening. So I think we're just about at the end of our session. I'm sorry we didn't have time to go to the laser.
Next time.
Next time, but we are, yeah. Laser is next time, maybe, when we actually have it working. Can we just check in with the control room and see how things are going? Is everything... I assume everything is fine. We're just plodding along on the transit.
Yep. Yeah, this is a kind of a rare, well, not extremely rare, but somewhat rare experience where we have a very long observation. So especially with this instrument usually, I mean, we can have one 45-second exposure and then have to slew. It takes longer to slew than take the data. But yeah, we just have this really long transit observation. So we're just kind of kicking back and watching the data roll in and making sure that it's good, good quality.
Yep, this is the best type of observing when nothing's happening. If things are exciting, it may not be good for science.